Okay, good morning, everyone. I've just hit the record button. So today I think is my favorite day of uh, all the classes. The 15 puzzle, the day where we sort of crack that open is a good one. But this one we will start to see how our work up till this point allows us to crack open pretty much all permutation puzzles. We've got enough theory now behind us that we can see how we can start to put this into practice. So I'm going to continue on with the commutators lecture from last day, but as opposed to what we did last day, where we did a lot of theory about commutators, and really the bulk of this was all about getting across this one point. And this now at the top of the page, this is the main point that says, if you want to know what a commutator does, what pieces it moves on a puzzle, it's easier to think about it that way rather than just as permutation. So let's think about it as actually being applied to a puzzle. So you do a move alpha and you do a move beta. What do you get? What pieces are moved if you do the commutator of those? So alpha, beta inverse, beta inverse. So the sequence of those four things in a row. What you get are the pieces that are affected are going to be the pieces that are in the intersection of both moves. So those pieces that have been affected by alpha and by beta, but also those pieces that got moved into that intersection by either alpha or beta. And that's what that formula at the top says. So that's the plain language description of that formula. What gets moved by a commutator? The things that get moved by each element of the commutator, the alpha and the beta, plus the things that get moved into that spot where by either of those moves. So the things that get moved into that intersection by either alpha or beta. And that's our picture, the thing with the three green blobs. The green blob in the middle, kind of like if you think of it as a face, like the nose is the things that are moved by alpha and beta. And then the two eyes are the things that are moved into that intersection by either alpha or beta. And that's it. That's all that gets moved. So we immediately know what pieces are going to be moved if we do a commutator of two move sequences. Okay, so we did a few examples, and then we did a few more examples, and now I want to do just a few more examples. We'll play around. Actually, I'm going to do these ones again, just for emphasis. I'll do it on the virtual version. So I'll bring the virtual version over. And the emphasis I want to make is, so I'll cover up the bottom one. We'll just do the corners. So what's happening? We're going to do these two moves. So in what we call a move X and move Y. So when we're trying to decide what the commutator of these two things will produce in the end, so do X, do Y, then do X inverse, then do Y inverse, what they will do in the end, it's a matter of what pieces both X and Y have affected when you do them individually. So Y is just an up move. So Y is, oops, I'm on the stickers version of this. Let me turn it to twist. There we go. Let's do a U move. So that's what the Y move is affecting, all those pieces in the up layer. Okay, great. What does the X do? So let's do the X. I'm thinking of this red as the front face now. So X is left, down squared, left inverse. And what I'm really interested in is what pieces did X affect that also Y has affected. So what pieces were both moved by X and Y, or what positions were both affected by X and Y? And the nice thing is we can just stare at the puzzle and say, well, based on the move I did, I can kind of peek around to see, yeah, those are all oranges and whites that are in the right spot. So the only thing in the up layer that got affected by X was this corner piece. So that is the only piece that got affected by both X and both Y, or that's the position on the puzzle that was only affected by X and Y. So that is the intersection. That's what we call move, in this case, move XY. So it is the intersection. The only other pieces that get moved on the puzzle when I do the commutator of X and Y are going to be the pieces that get brought into that intersection. And so because I've done the X here, I can see immediately what piece got brought in there. It was the green, yellow, orange piece. So I look around the puzzle, for the green, yellow. So there's green face, yellow face, orange face. So it was this corner back here. Oops, this corner back here. So I'll reorient our puzzle so that the red's in front. So it was this corner piece back here. That's what X brought into there. What does Y bring into that? Well, if Y is my up move, then Y is going to bring this piece into that corner. So at this point, with only doing the X move and staring at the puzzle, I know exactly what pieces the commutator between X and Y are going to do. It's going to affect this corner, and this corner way back here. Because this is the intersection, this is what X brings to the intersection, and this is what Y brings to the intersection. And that's what our theory of the commutators and their move sets were telling us, was that the things that get affected are the intersection and what get brought into the intersection by each of the moves respectively. So then we can go ahead and do that. I've done the X, I do the U, I do the X inverse, which would be an L D squared inverse, which is the same as D squared, L inverse. So now I've done X, Y, I've done an X inverse now. Now I just need to finish it off with a Y inverse. And we see, just by glancing around the puzzle, that those are precisely the three pieces that got affected. So in building moves for these puzzles, what we do is we look for sequences. And in fact, for most of us, it's just going to be one longer sequence commutator with one of the basic moves. So in this case, a longer sequence that only affects a couple of pieces at most in the upper layer, because then when I take the commutator with Y, I know exactly what's going to be affected, those things in the upper layer of the intersection and the things that get moved to the upper layer. So that's that first bit that says, okay, we've now got the ability to 3-cycle corners. And this is great because if we think back to our experience with the 15 puzzle, once we knew how to 3-cycle pieces, then we could attack any even permutation because we could just do 3 cycles to restore any even permutation. So this alone tells us, hey, we got a lot of progress already made on the Rubik's Cube now, because we can restore any even permutation of the corner pieces by doing 3 cycles. Okay, so you might say, well, all we know how to do is cycle these 3 corner pieces, 2 next to each other and 1 far away from it. Well, we'll see later on today that we can modify this and really get any corners we want. And that's the next chapter on conjugation. Okay, so let's restore this and look at the next. The next one is, I'll scroll it up a bit, is now corner rotations. So how do we rotate corners? Well, the basic idea is to try to come up with a move sequence that rotates only one corner in the up layer and leaves every other thing in the up layer fixed, just doesn't touch it, leaves it alone. Because if I can do a move sequence that only rotates one corner piece in the up layer and leaves everything in the up layer unchanged, while possibly screwing up the entire bottom 2 layers, it doesn't matter. I don't care if it messes everything up in the bottom layers, just as long as it does the one thing to the corner I want in the up layer and leaves everything else in the up layer untouched, that sets it up perfectly to be a commutator with the U move, because the things that would get affected are the intersection. And if I've made my first move X appropriate, then that intersection is just going to be that one corner QB that I've twisted. And all the things that get brought to that corner. So let's do that one move sequence that, let's say, rotates this corner here. And I'm going to do that way that I did on Monday, and that was to think in terms of elevators. How am I going to rotate this corner? Well, I'll bring it down with one elevator, and then I will pick it up with the other elevator. I'm thinking of a left elevator and a front elevator. So I bring it down on one elevator. Then I get it completely off that left elevator, but I also need it completely off the front face because I want to use that as another elevator. Right now it's sitting here, so I do one more twist. That's the D squared in the move. And then I restore that left side. So what I've done is I've brought the elevator down, got that piece completely off of it, and restored everything. And now I'm going to use the front face as an elevator to pick it up. So bring the elevator down, load it in, send it up. And what it's done is it's ultimately rotated that while possibly messing everything else up in the bottom 2 layers. Doesn't matter. I don't care about that, because my theory tells me that if I do a commutator of this and an up move, That's my up move. The only pieces affected are the intersection, which of all the pieces in the up layer, the only one that got affected by the X move was this one that I'm staring at. That's why I like to do the long sequence, the X move first, just look and go, okay, that's the piece that got moved. Everything else in the up layer, yep, it's all good. So this piece will get affected by the commutator, and what gets moved to that location by those two moves, X and Y. What gets moved to it? Well, X didn't bring anything new there. So it's still just that one piece that's only affected. What does U bring to that new location, or to that intersection location? It will bring this piece here. So there's my U move. So I know that if I do the commutator of the X move, which I just did, and the U move, the only pieces that'll get affected is this corner piece and that corner piece. And in fact, I know even more, because what I'm going to do is I've done a move sequence X. It rotated this corner piece clockwise. The blue was on top, now it's on the right, so it kind of rotated it clockwise around that vertex. When I swing this new piece over and undo the X move, what it's going to do is it's going to rotate this one counterclockwise. And then we slide it back. So what we will have done is we'll have created a move that rotates one piece clockwise and one piece counterclockwise. So let's go ahead and do that sequence now. So I've done the X move, now I do a U, and then I do the X inverse move. So I just go backwards on it. So I like to think about this as front elevator and left elevator. So my setup move, my X move, was left elevator, then front. So to undo it, I use my front elevator. Get it off of there, restore the front elevator, now bring the left elevator down, load the piece in, ride the left elevator up. So now I've done X inverse, and then I do U inverse. And now I've got a move that rotates two corner pieces next to each other. In this case, they're adjacent corner pieces, one clockwise and one counterclockwise. And the idea was the bulk of what I had to do was just in building X. Once I built X, that's it. Everything else flows from that. X, Y, X inverse, Y inverse. That's just a commutator. So I only had to focus on, hey, I want to rotate some corner pieces. I'm just going to figure out how to rotate one corner piece in the up layer while it messes everything else in the bottom layers. And I don't care about that because those will get restored when I do the commutator. They're not in the intersection. They're not being moved to the intersection. So this is basically, now we can deal with corners on the Rubik's Cube. We know how to 3-cycle them, and we know how to rotate them in pairs. And that's really all we need to know. We need to do the same thing for the edges, and we'll see that in a little bit. But I want to do a little bit more now with this. Commutators. Do a move, do another move, undo, undo. That tends to be the key. So what we have now is the key to understanding permutation puzzles as a whole. So if there's any class in this course that you want to walk away from going, wow, I just used math to understand a whole collection of puzzles, it's this class. This is it. This is where everything comes down to. So let's see why. I'm going to just go through a series of puzzles. So here's the pyraminx. So this is the basic move on a pyraminx. We can rotate tips, we can rotate the middle layer, and we can rotate the last layer. So it's sort of like a face rotation of one of the tetrahedron faces. And whenever we grab a new puzzle, the first thing I always do is I just do commutators. I just go, okay, there's a move, there's a move. I'm going to do the commutator of the two. One, so move one, move two, inverse, inverse. And then I look to see what happens. And there we go. We built a 3-cycle. We got a 3-cycle on the puzzle. And if you play around with this a little bit more, you'll realize that really that's all you need to know how to solve this puzzle is a 3-cycle. And we're done. That's it. Now, the fun thing about this is, okay, you do it again. So I did this one first. So I went like that. So I do a 3-cycle again. Okay, it just 3-cycled them. Then I do it one more time. It restores. So we got a 3-cycle. Now what we'll try is maybe something like this. I'm holding it with the red face down. So 3-cycle. And you'll notice that what happened was the piece that was here jumped across here. And that was the 3-cycle. Then it went in a clockwise direction. But this piece, as it jumped across, it kept the yellow face towards me. Whereas the other two pieces, when they jumped across, they essentially flipped. that's interesting, because what it means is that I could do a 3 cycle and it looks like a couple of pieces get flipped. So let's see what else we can do. If I take the whole puzzle and I rotate it, so I do a full puzzle rotation, then what I'm going to do is I'm now going to undo that 3 cycle that I just did. These pieces still got cycled in the clockwise direction, but now I'm going to undo them. To undo them, this week's assignment says, if you want to undo a commutator, you just do the commutator with the X and Y reversed. So I use this move first. So if I want to do the inverse of the commutator, I do this move first. So let's do that. And I would have cycled those pieces back. Yep, yep, and yep, they got cycled back, but there's a flip now. So this is in the right location, just the wrong orientation. This is in the right location, wrong orientation. So now I got a move that allows me to flip 2 edge pieces on the Pyraminx. So now I have a 3 cycle and a move that allows me to flip edge pieces. And they were all just built by doing a commutator of these 2 moves with the possibility of rotating the entire puzzle. So we basically at this point have complete understanding of this puzzle. It'll take a bit to see why it's complete understanding, and that's sort of more theoretical development. So we're building moves, and at some point you have to decide, have I built enough moves to completely solve the puzzle no matter what configuration I get? And we've done the building of moves. Now we have to do the theory to see, is this enough? And so anyone who's doing this as a project, that's certainly what you can do for your project. You can do the analysis of the theory at that point. I might have just given you a hint as to how to build moves. What else can we do? I'm going to take this puzzle now. This is what's called the Skewb. And so what the Skewb is, it's a puzzle that, I don't know if you can sort of see what's happening here, but it's rotating around an axis through the 2 vertices. So a diagonal axis through the 2 vertices, and exactly half the pieces are moving. So if I'm holding it back here and I do this, exactly half of the pieces are moving. 3 centers, 4 corners are all moving, and the other half of the pieces are stationary. So this, some people think, well, that's a lot more complicated than the Rubik's Cube, because for the Rubik's Cube, like a third of the pieces are moving in some sense. It's like one of the slices, but this one, half of them move on every turn. Okay, so it might be a little bit more complicated, but let's just see what happens. So what I'm going to do is I am going to hold it in such a way, maybe I'll hold it with the red face towards us, blue face on top, and I'm going to pick this corner as my vertex that I'm going to rotate around, and I'm going to pick the one next to it as a vertex I'm going to rotate around. And then I'm just going to do the commutator of those 2. As I said, this is sort of one of the very first things I do whenever I pick up a puzzle, is just look at the basic moves. Okay, that's a basic move. Basic moves are rotations around the vertices. Okay, fair enough. And then I just pick 2 of them and do the commutator and see what happens. So we'll do the commutator. First, I'll rotate about that corner. Then I'll rotate about this corner. And then I'll undo. And then I'll undo. And sometimes I glance around and I'm like, ooh, a lot of stuff got messed up. Okay, I'm not worried about that. I'll just do it again, see what happens. So I do the commutator again. 2, inverse, inverse. And we know through our theory that if we just keep doing the same move over and over again, we'll get back to the solved state. So it's really a question about, does interesting stuff happen between when I started in the solved state and when I ended in the solved state? So I've done 2 moves now. And now I look and I say, I started with blue on top. Okay, blue center's on top. I had red on the front, red's still on the front now. Yellow's on the side. So all the center pieces are back where they're supposed to be. This corner piece is supposed to be the blue, red, yellow corner piece. Blue, red, white corner piece. It is the blue, red, white one. It's just been rotated. That's supposed to be the blue, yellow, red one. It is. It's just been rotated. Similarly back here, these were just rotated. What direction were they rotated? This one rotated clockwise. This one rotated clockwise. This one rotated counterclockwise. this one rotated counterclockwise. So I got 2 clockwise rotations, 2 counterclockwise rotations. And if you do a bit of theory of this, you'll see that this is really all you need to know how to do to orient corner pieces, because there's part of the theory that tells you, and we'll do the analysis for the Rubik's Cube and the like, but there's part of the theory that will tell you that how corner rotations have to appear. Do they appear in pairs? If so, do they appear, and all of the like. And this turns out to be the move that you need in order to set the corners. So that's good. So we did that basic move twice. Let's keep going. So 1, 2, so I'm doing it for a third time, the commutator for a third time. And I see, oh, all my corners are back where they started. That seems reasonable, because when I did it twice, it was a rotation. And so when I did it a third time, it must have been the third in a series of 3 clicks to get them all back where I started from. But now I look at my centers and I'm like, oh, those 2 have swapped. And these 2 have swapped. So what I've been able to do is produce a move that swaps 2 centers and in pairs, the top and the front and the left and the right. And then I just keep going. So that was rotations of corners, swaps of centers. So that's my 4th move, my 5th move, and lastly, my 6th time doing the commutator. And I'm back to where I started. And if anyone's picked this puzzle, I'll leave the rest of the presentation for you, for your project. But that's the idea, is we just did a commutator, we did it repeatedly, and we started to uncover things that happen. Small number of pieces got moved. Couldn't we just, no, so that's a good question. Could I rotate a corner piece on this one? Nope. And in fact, this one might not come apart too easily, but my other one does. So anyways, the corner pieces don't rotate. It's the full rotation on this case. Yeah, so that's a good question. So that's basically that one. Pick up another puzzle. This is a cube where the moves are rotations about vertices. So it's rotations about a corner, and it rotates the corner piece as well as these edge pieces. These edge pieces all move as well. And then I look and I say, well, if that's a basic move, and I take that basic move about one corner, this basic move about another corner, the intersection is this piece. What gets moved to the intersection is that piece. The other move brings this piece to the intersection. So if I do the commutator of this and this, I know it's only going to affect the intersection and the 2 pieces that get moved to the intersection. So let's do it. Move 1, move 2, inverse move 1, inverse move 2. And there is a 3 cycle. So now I've got a 3 cycle on this puzzle. So, we're starting to crack our way through these puzzles. It's just like, oh, okay, just commutators is really what I need in order to get a handle for what's going on. Got another puzzle here. This one's always a fun one. There's some moves that when you do them, they actually remain in the solved state. So this is one that's got more than one solved state. If you were to number this like 1, 2, 3, all of these are solved states. What could we do? Well, there's a rotation about the vertices. That's a move. And as I've shown you here, there's rotations of the faces. And those are the 2 types of moves. You can rotate around a vertex, or you can rotate around the face. So what we'll do is we'll do the combination of those 2. So I'll do a rotation around a vertex. That's move 1. A rotation around a face. That's move 2. A rotation around the vertex, the inverse one. That's move 1, inverse, and then move 2, inverse. And I look and I see, oh, that looked like a swap of 2 pieces. So I got to move that swaps 2 pieces. Something's wrong here. Can anyone tell me what's wrong? You might say, what do you mean by what's wrong? So let me just grab something here. I'll let you ponder for a second, and then, sorry, I'm just looking through my files because I just got to grab a, I thought as usual, I thought I had something open and then it wasn't open. So, beautiful. Yes, that's what I like to see. No swaps allowed. Each move is a 3 cycle, but a swap is a 2. So that's right. So it looks like we've done a swap. Why could I not have done a swap? I did a commutator after all. So what's special about commutators? And whenever we're trying to show things are impossible, think parity. Always think parity. Why would a swap be impossible to do if I was to do a commutator? Any ideas? Exactly. Question, that's what I was looking for. I was like, which question on the assignment did I do this? It was question 1A, right at the start. Question 1A of this week. Show that the commutator of alpha and beta is an even permutation. So we just did a commutator. Commutators are even. So what I would have done is an even permutation. But it's like, whoa, wait a minute. I didn't do an even permutation. I did a 2 cycle. And the thing is that actually it is an even permutation. You just aren't able to see the fact that one of these other red pieces was in the mix as well. So I'll do it again. What we did was, so right now it looks like it just swapped these 2 pieces. So the first move, I'll do the commutator again. So it was vertex move, the face rotation, undo the vertex move, undo the face rotation. And now we see that, oh, that piece actually was involved in the mix. So it's really these 3 pieces. And it's not surprising that it's those 3 pieces. And that's because what's happening is I'm doing a commutator with that and this. So that is the intersection. What gets brought to the intersection? Well, the first move I did was this. So that piece is getting brought to the intersection. The second move I did was this. So that piece is being brought to the intersection. And so the intersection and the 2 pieces that get brought to the intersection are precisely the ones that are going to get involved in the mixing. And they're the ones that the commutator is going to affect. And so what we have is that those are precisely the 3 pieces. We just didn't notice it the first time around because what happened was when we cycled these pieces, the green jumped from here to here. This piece, which was red, went to there, which was already a space where a red one occupied. So we didn't even notice it changed. And then this red one came up here. So if we do it again one more time, everything gets restored. So it was a 3 cycle. So for example, if I wanted to involve, if I wanted to see that things are really happening, maybe I'll move a white piece there. So our 3 cycle would actually involve these 3 pieces. So I'll do it again. Vertex move, face move, undo vertex, undo face. And those are precisely the 3 pieces that ended up getting cycled around. So again, commutators, that's the key. That's the golden key. So basically in this course, what we've done is we've handed over the key that allows you to unlock all these puzzles. And now what you do with that key is really up to you. Yeah, exactly. This is exactly like the goat puzzle, where you can swap 2 pieces because you use the fact that, I shouldn't say you can swap 2 pieces, where you give the illusion of swapping 2 pieces, but you can actually swap 2 identical pieces somewhere else and give that effect that you've only swapped 2 pieces. I'm still not done. I've got a long, I got a whole whack of puzzles here. I've just picked ones that I thought would be fairly interesting, just off the. So that are easy to understand in the sense that I can just show you what the move is. If I grab some more complicated puzzles, then we have to walk through what all the possible moves are. But in this one, this is a cube. We're rotating around a vertex, and there's just the corner piece, and then what are 3 face pieces that are wrapping around. It's kind of like the skew, but in this case, it's the corner the three faces, but this one is also cut deep enough that it also brings the other corners into the mix as well. Whereas this one is cut very shallow. In fact, it cuts right through a corner. So there's no corner pieces, additional pieces that are moving around. So I'll do the same thing with this one. I'll pick two moves. In this case, they're going to be opposite vertices from each other. And what I'll do is I'll just do the move sequence where I rotate one and I rotate the other. And if I look closely, I just try to see what is the intersection of this one and this one. It's just that blue piece. So when I do those two moves, this and this, it's going to be their intersection and what gets moved to their intersection. So I will effectively produce a 3 cycle on these. So let's do it. So move 1, move 2, undo move 1, undo move 2. And we've got our 3 cycle. And so now, if you sort of think about this puzzle, the corners aren't actually going anywhere. They're just rotating around themselves. So if we've got a scrambled up version of this puzzle, let's say, I don't know, I'll scramble it a little bit here. If we got a scrambled up version of the puzzle, then what we have to do is just see if the corners are properly oriented. So yellow, yellow, good. So that's the yellow face. So, oh, there's an orange face. There's the green face. So this last one here, maybe I'll do a couple more twists to make it a little bit more challenging. There's not much challenge to this puzzle, so that's the main point. Okay, so I'm looking at this one and I'm saying, there's a yellow, blue, and an orange face here. So I'll look at the corner opposite it, and it only shares one color in common. That's the yellow. So that means that this is the yellow side. And so then I'll go across and say, if that's red, then this has got to be the red side. Oh, there's the red. And if this is green, then that's got to be the green side. And there's the whites matching up. And so all my corners are solved. So corners are done. Now we just need to solve the centers. And now we've got a 3 cycle to do that. So I've got a 3 cycle that allows me to cycle things around. In this case, maybe we'll look at this one first. So there's 3 colors. I need them to cycle around. So white goes up top. So we'll go ahead and we'll put white up top by doing a commutator. And now that leaves me with these 3. And then I go ahead and I scan around. Okay, there's another 3. I need that green to go up top. So I'll do the commutator of these ones. And that put green up top. And I keep scanning around. Oh, now I've got 3 along the band. Okay, with 3 along the band, how am I going to deal with that? Well, actually, with the 3 along the band, I'm going to leave this, because if somebody wants to do this one as their project, if someone hasn't picked a project yet and wants to do this one, then those are the kinds of questions you want to ask. But so we're starting to develop the ideas that with commutators, we can build moves, and then we can use those moves to crack these puzzles wide open. I think that's probably enough for examples for now. Let's see what else we've got. The oval track puzzle. So with the oval track puzzle, the idea is, so this is going to be in chapter 15. We'll completely analyze the oval track puzzle, but now we're just getting a start on a whole bunch of puzzles. So just like the ones I just demoed, let's do the oval track puzzle. Let's see if we can build a basic move on this. The move T moves every thing on the turntable, 1 through 4. The move R. So good question, Ompreet. Are the commutators the same as A, B, A inverse? No, those are called conjugates, and that's the next chapter, which we'll actually cover today. So commutators are A, B, A inverse, B inverse. Knocking off the last B inverse and just focusing on A, B, A inverse, those are called conjugates. So commutators allow us to build new moves. What we'll see is conjugates allow us to modify existing moves. So the reason conjugates came up in the 15 puzzle is because we knew how to do 1 3 cycle, and we wanted to modify that move to build other 3 cycles. So modification of moves was conjugation. Building moves is commutators. And if you want to think about where the original 3 cycle comes from on the 15 puzzle, it is basically, let's see, we've got our 15 puzzle, we've got our corner here, maybe this is the empty space, and I want to 3 cycle the tiles around. I could do a down and then a right, and then an up, and then a left. And that is do a move, do another move, undo. So that's like a D inverse, and then undo. That's like an R inverse. So that our basic 3 cycle on the 15 puzzle was a commutator, DRUL. And we modified it by using conjugation, which is the next chapter. Yeah, good question. So the way I like to think about it, commutators build new moves. Conjugation, modify existing moves. And we haven't stated what a conjugate is, but basically that's the things that we've been doing. And I had you do experiments with on Sage as well. It was the A, B, A inverse. So for the oval track puzzle, what I'll do is I'll proceed as follows. I'll just say I want to have 2 moves that have minimal overlap. So one move, I'll circle it on here. One move is to just do the turntable on all of these, 1 through 4. Now I want another move that has minimal overlap. One way to think about another move that has minimal overlap is to just say, well, I can really turntable any 4 tiles. Any 4 tiles, I can always rotate them around the track into the turntable them, and then rotate them back. So I could turntable these 4 here, 4, 5, 6, and 7. How would I turntable them? I'd rotate by basically R. I'd do an R to the -3 to do 3 clicks in the counterclockwise direction, then turntable them and rotate them back. So what that means is I could do a R, so maybe I'll rotate, I'll do the green ones first. So R to the -3, turntable them and rotate them back. That would be the move that would do the effective turntable move on these 4 numbers. Rotate them into the turntable them, rotate them back out. And then I could do the turntable on the other 4. And then they've got minimum overlap. The intersection of these 2 moves would be the position that's affected by both, which is that one, and the pieces that got moved to the intersection. The first one moves the 7 there, because that's sort of our moving around and then turntabling and moving back, and the other one brings that piece there. So if I was to do the commutator of these 2, I know it's only going to affect 1, 4, and 7. So we'll do a comma with a T, and that's going to affect 1, 4, and 7. It turns out, that if you do this, let's write it out, R -3, T, R3, T, and then the inverse of that first one, which is R -3, T, R3, and then T again, just because T is its own inverse, that this also looks like a product of 2 commutators. It looks like the product of R -3 and T squared. So with itself, it's just 2 commutators being done back to back. So I could think of it as 1 commutator, or I could think of it as the square of a commutator involving the basic moves. And that's the one I've written down up above. So let's see what it actually does. I'm going to bring over our oval track. So the move I'm going to do is R -3 T, and the commutator of those. So R -3, 1, 2, 3, T, and then the inverse, which is R cubed, T. So what happened? 1, the piece that was in 1 now went to 4. The piece that was in position 4 went to 7. The piece that was in position 7 went to 1. So there's a 3 cycle, 1, 4, 7. But 3 and 2 have swapped positions, and 6 and 5 has swapped positions. And that's what I've written down here. What is R -3 T? It was a 3 cycle, 1, 4, 7, and then 2 2 cycles. So if I square it, then I just get the square of the 3 cycle, because it kills the 2 cycles. And so that gives us our 1, 7, 4. And so that's another way to look at it. I can look at it as a commutator of R -3 and T, or I could look at it as a commutator of turntabling the first 4 numbers and then turntabling numbers 4 through 7. Either way you want to look at it, you get the same result. And that is a 3 cycle, 1, 7, 4. And so we got a basic 3-cycle on this puzzle. If you know a 3-cycle, you can probably use it to get all even permutations. And so that gives us a pretty good advantage on this puzzle. We know that all permutations are possible. Sage told us that the number of permutations is 20 factorial, which is all of them. But now we've got a way to solve at least all the even ones, because we've got the ability to do 1 3-cycle. And much like the analogy with a 15 puzzle, if you can do 1 3-cycle, you should be able to modify it to do more 3-cycles. And that's what I want to get to now, modifying. So that's our conjugation section. This is now modifying. We've created moves from scratch using commutators. Now what we want to do is we want to modify existing moves. I've referred to it as creating new moves from old ones. So once we know how to do some commutators and create some useful moves, now we can create modifications of those using conjugation. So let's just see what this actually is in practice. So for the 15 puzzle, we had this 3-cycle that allows us to go 11 tile in position 11 goes to tile in position 12, and tile in position 12 goes to position 15, and tile in position 15 goes to position 11. So we were able to produce this 3-cycle. That was the most basic one we had on the 15 puzzle. Let's try to produce this one. And this, I know you're all experts in this by now, because the midterm really showed me that you're all experts in this. And so that's wonderful, because this is our building block for moving forward. So what are we going to do to build that 3-cycle? Let me just find my '15 puzzle. I'll just minimize it a little bit. So the one thing I'm going to note is that I want to use an existing 3-cycle. So the 3-cycle that's in the 11, 12, 15, 16 2x2 array. I'm interested in producing this as a result. So I'm going to think to myself what I want from the solve state to get to here. I want tile 15 to chase tile 13. I want it to go to where tile 13 was. So if I think about, if I'm starting with this position, I want the 15 to go here. So I want 15 to go to where 13 is. And that's all I'm going to think to myself. Tile 15 is going to go to where 13 is. So now I'm going to build the move that cycles 13, 14, 15. The way I'm going to do it is I'm going to bring them all together. And maybe I'll just keep going around the track like this. So I'm just going to cycle like a snake around the track, bringing them all together. Something like that with the empty tile there. I know how to 3-cycle pieces in this position. What I want is 15 to go to where 13 is. So I'm going to cycle them in the opposite direction here than what I've listed. Here I've listed the clockwise 3-cycle as 11, 12, 15, but we can do the counterclockwise 11, 15, 12 just by cycling in the opposite direction. So I want 15 to go to where 13 is. So I'll do my fundamental 3-cycle that I have on this puzzle. And now once I've done that, now I will undo that setup move. And that's just bringing them all around. And there we go. We've done our 3-cycle. So what we've done, I'll write it down here, is we've done a 3-cycle that effectively looks like this. We've done an R, 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 D, L, 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 U, R, R, D, L, L, U. That was basically move tiles 13, 14, 15 into boxes 11, 12, 15, 16. Basically bring them all together and then do the fundamental 3-cycle that we know how to do. In this case, we did the inverse of this one. And then we undo our setup moves. And that means just do the inverse of what was listed there. So I'll write it out again, but in this form, because it's the structure that I'm interested in. So that's what we want to exploit. We want to exploit structure. So we set up, 3-cycle, undo our setup. This is what's called a conjugate. This is what conjugation is. It's taking some permutation. It doesn't have to be a permutation, just any element in a group where you got an operation, so a group operation, and you just multiply the front and back by an element in its inverse. Let's see how we can use this kind of idea to do this kind of a move. Take the Rubik's Cube, which we know how to 3-cycle in this way, and now do a move which 3 cycles all of the ones on the same level. How do we do that? Well, if I can 3-cycle this one, and the one back here, then what I can say is if I really want to cycle these 2 in the front and this one back here, the very first move I'm going to do is take this one I want to bring into the mix and just send it down to this corner. So that's like my first move, my setup move. That's like bringing all the tiles into the right spots. Now I do my 3-cycle. So my 3-cycle was left move, down squared, left inverse, and then up, and then undo that first move, and then undo that second move. So now I've done the commutator, which 3-cycled, and now I undo the setup move. That's like send all the tiles back now. And there we go. We've got our 3-cycle, which involves all corners on the same layer. And that's this idea of conjugation. So I will get to the definition of conjugate, and then we will prove the theorem. And that way you'll be all set up for the homework assignment questions, the last 2 questions of this week. So the definition of a conjugate is if you have 2 elements, G and H, that are in a group, we call the element, which is H inverse times G times H, the conjugate of the thing in the middle by the thing we're sandwiching it by. And in this case, we just want to make note of the order. When we conjugate by H, we multiply by H inverse first, and then G, and then follow it by multiplication of H at the end. Yeah, so that's a good point, William. What's with the G to the power of H? This is a shorthand for H inverse G H. So that's how we can do it, by writing essentially 3 less symbols. We don't have to write a negative, we don't have to write a 1, and we don't have to write the second H. So that's just a shorthand. And you might say, well, why did you choose that as a shorthand? It turns out that conjugation has a lot in common with the rules of exponentiation. And so that's why this notation was chosen, because the notation starts to suggest properties that the conjugate can have. But it's for right now, is all that we just need to worry about is that if I write G to the power of H, it just means that's shorthand for H inverse GH. So let's see what follows from this. So what happens if the conjugate of G by H is equal to G? What does that mean? Well, what that means is, let's write out what G to the power of H is. It's a conjugate, so it's shorthand for this. If that is equal to G, then multiplying both sides on the left by H, we get that. There we go. Multiplying both sides on the left by H, we get that GH is equal to HG, or in other words, G and H commute. So the conjugate of G by H is not going to give us anything new. It's just going to be G itself, only when G and H commute with each other. When they don't commute with each other, that's when conjugation comes in handy and starts giving us useful things. So that's another reason why conjugation probably wouldn't have been seen in other courses, because in most of your other courses, things always commuted. So you'd never use commutators, you'd never use conjugates. But as soon as you have non-commutativity, then conjugates and commutators come in handy. We say 2 elements are conjugate if one can be written as a conjugate of the other. And everything that's conjugate to a particular element is called the conjugacy class. So those are just a couple of definitions, not much more really needs to be said about that. But here's the big thing. Conjugation preserves cycle structure. So I do want to wrap up with this, because this is basically the final connection with assignment number 4, which you did many weeks ago. This last question, explorations in Sage Math. Fill out this table. Now, starting with alpha, do the beta inverse alpha beta of alpha with this beta for random betas. So in other words, you were computing the conjugate of alpha by beta. And what you got was the cycle structure was exactly the same. And it turns out that this is the theorem that we're now presenting, that the cycle structure will be the same. Moreover, where did these numbers come from? Those numbers came from these numbers, and they are precisely obtained by doing the following. If I take the number 1 and I look, what does beta do to 1? Beta takes 1 to 15. So 1 gets replaced by 15. 2 gets replaced by 8. So it would be a 15, 8. 3, beta takes 3 to 13. So it would be a 15, 8, 13, and 4, beta takes that to 11. So it would be a 15, 8, 13, 11. And that's precisely the cycle we get. So that's what this theorem is telling us. Not only do we know what the cycle structure is, we exactly know what the values are. That's this result right here. And so the proof of this is, there's the first part that says, suppose alpha takes I to j. What does alpha to the power of beta, or the conjugate of alpha by beta, do? Well, the claim is that it sends beta I to beta j. So let's check. This is some number. Beta I is just some number. What does it do to it? This is beta inverse alpha beta of beta I. This will explain now why the conjugate has the inverse of beta first, why it's beta inverse alpha beta. And that's because when we apply this function to beta of I, we do the beta inverse part first. Right, we're applying the composition of beta inverse alpha beta. That means do the beta inverse first, follow it by the alpha, and then follow it by the beta. And then we just work out what this is. This is I. So then this is alpha of I. And what is alpha of I? Alpha I is j. And so this results in being beta j. And so exactly what we wanted to show, oh, I already had a check mark there, exactly what we wanted to show, that the conjugate of alpha by beta, if alpha took I to j, if I goes to j in the cycle structure for alpha, then that gets replaced with beta I going to beta j for the cycle structure for the other one. And then part B is the last part that says we get the cycles exactly in this form. And the way we're going to do that is we're going to say, since beta inverse of a product of cycles times beta is beta inverse sigma 1 beta. I can insert all of these beta inverse betas between everything. That means we only need to prove the result for a single cycle. We just consider alpha as a single cycle. And so then we go ahead and we have to work out that for a single cycle, beta inverse of A1, A2, dot, 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 all the way up to AK of beta. When we conjugate a single cycle, it just produces beta A1, beta A2, all the way up to beta AK. And I'll say see details in text. That is the result that you found experimentally, that when you conjugate a cycle, it just updates the numbers by beta. And so that's what you need in order to do the current week's assignment. So we're all up to speed. So I'll stop the recording.